The equilibrium constant, Kc. A mathematical relationship provides a constant value for a chemical system over a range of concentrations. It is not limited to one set of initial conditions like a percent reaction. In this mathematical expression, A, B, and C, and D represent chemical entities or species, and lowercase a, b, c, and d represent their coefficients in the balanced chemical equation. Coefficients become exponents of the concentrations of the species, and concentrations must be measured in moles per liter. As you can see, the Kc equilibrium constant is calculated by having the products divided by the reactants, the coefficients being their exponents. Let's try an example. Write the equilibrium law expression for the reaction of nitrogen monoxide gas with oxygen gas to form nitrogen dioxide. A balanced chemical equation with whole number coefficients is used to write the mathematical expression of the equilibrium law, as the coefficients of the balanced equation becomes the exponents of the concentrations. Remember that equilibrium constant is products over reactants, and the coefficients are their exponents. It is therefore very important that before you do the answer, make sure that the equations that you have is completely balanced correctly. Once we calculate the equilibrium constant, we will ignore the units and list only the numerical value of an equilibrium constant. The higher the Kc value, the equilibrium constant, the more it favors the forward direction, the more products will be produced. The value of the equilibrium constant depends on temperature and large changes in equilibrium. A moderate change in the concentration of any one of the reactants or products results in a change in the other concentration, so that the equilibrium constant remains the same. The equilibrium constant provides only a measure of the equilibrium position of the reaction. For example, if the Kc value is greater than 10 to the power of 10, we mentioned that it is a quantitative reaction, meaning that greater than 99% of the reaction is happening. We will completely use up all our reactants and make a product. If I have a Kc value bigger than 1, more than 50% of the reaction is happening, meaning products are favored, forward is favored. When we have a Kc value less than 1 in decimal values, we note that the reactants are favored and 50% of the reaction, less than 50% of the reaction is happening, meaning that there's more reactants left instead of making products. If you have a Kc value that's very minute, 10 to the power negative 10, we regard it as not taking place at all. So no products are being produced, that the reactants didn't collide or have enough energy or wasn't in the proper orientation. Note, Kc does not provide any information on the rate or speed of the reaction. Let's give you a practice problem. Stop the video and then I will show you how it's solved. You can do this on your own for the next 2 minutes or so. Now, for the solutions. First, we need a balanced chemical equation, balanced numerical coefficients. Remember that Kc value is products over reactants. Then we substitute the values in the expression. And then we calculate the Kc values, proper significant units, digits, and no units. Hopefully you got the right answer. Very important to note that solids and water liquids are not included as part of your equilibrium expression. Substances in the gaseous and dissolved state aqueous have variable concentrations, meaning that their amount of concentration is changing and must always be shown in the equilibrium law expression. So, to reiterate, solids and liquid water species are not included in the expression. only gaseous and aqueous species are put into our equilibrium expressions. Please read the summary and make sure you understand its components. Let's do a practice. Okay? We expect you to be able to do the following when we interpret what the Kc value means. Give you about a minute to figure this out before I show the answers. Hopefully you've tried it on your own and see if you got the right answers. Having a Kc value of 2 means that the reaction favors the forward or makes more products, and that the percent reaction gives you more than 50% yield. And if you have a 0.0020, the reaction favors the reverse, favors the reactants. Okay? Less than 50% products are made, so there's more reactants left, so on and so forth. Here are some more practice. Okay, so write the equilibrium constant expression for the following equation. Again, stop the video, and then I will show you the answer next. First thing that we do is make sure we note all the states that must be included. So since all of these are gases, all of these are going to be added in my equilibrium expression. There are no solids, there's no liquid water, so everything is involved in my equilibrium expression. Therefore, we need to look at products over reactants, making sure that their coefficients becomes exponents. So here are my products. My chloride and my water gas are going to be my products. My oxygen gas and my hydrochloric gas is going to be my denominator. Let's do some more. Here again are the questions. Stop the video and then I will show you how it is solved with explanations. So let's note that all the values given is at equilibrium. So all these concentrations are equilibrium. Therefore, these are the values I will put into my Kc value. If all the information are equilibrium concentrations, I do not need an ICE table, because all the concentrations at equilibrium is all that I need for the Kc value to be calculated. So let's do A. What is the value of the equilibrium constant for this expression? So products over reactants, products divided by reactants, exponents are their molar coefficients. Then I do a substitution. Then I note the answer in proper significant digits and no units for the Kc value. Let's do the next question. Determine the Kc value for the reverse reaction. Make a note that we have a forward reaction above here, and now we have the reverse reaction, which means that I will have different products and different reactants. They will be in the reverse. Notice that now hydrogen iodide is a product, whereas hydrogen and iodine are reactants. So in order to calculate the Kc of the reverse, I need to find the equation in reverse so that I know which ones are products and which one are reactants. Just like before, I place products over reactants in my reverse reaction, do my substitution, and get 54.4. Now, a second way of doing this is noting that the reverse reaction is 1 over the forward reaction. So I can use my value from A and do the inverse 1 over to calculate my reverse Kc value. Again, since this substitution is the inverse of this substitution, I could just make a shortcut and inverse my former answer to calculate and make sure I get 54.4. So you decide whether you understand the second component or do it the long way and understand it from products over reactants using the reverse reaction. Either way should give you the same answer. Let's do another problem. What is the equilibrium concentration of sulfur trioxide gas in the following reaction if the equilibrium concentration of sulfur dioxide and oxygen gas are each 0.05 moles per liter and given the Kc of 85.0? Note that all the information that is required of us are about equilibrium concentration. Therefore, we don't need an ice table because everything here is about the equilibrium. No ice table is necessary. This problem as well has given us the Kc value. We don't need to calculate it. We are given it. We just need to find the equilibrium concentration for sulfur trioxide, which is over here, which is a product. So first, we need to find the expression, products over reactants, based on this equation with their molar coefficients used as exponents. Next, we substitute all the values that is given to us, so I've underlined them in here, of what's unknown and what is given. Next, I do some calculations. I cross multiply so that I can isolate sulfur trioxide. Then I will square root both sides because this is a squared value. To get the concentration of sulfur trioxide, I get a value of 0.103 moles per liter. Okay. Make sure that you show all your steps so that you know where you will get it wrong and where you will get it right. Okay, so you can check your answers all the time for your process. Let's do another one. Determine the equilibrium concentration when only the initial conditions are known along with the equilibrium concentration of only one of the species involved producing an ice table. So here, we have an initial condition, which means that we need an ice table because not all the information given to us are equilibrium. Remember that we can only use Kc when we have equilibrium values. And at this stage, they've only given us one information for equilibrium. The rest of the information are initials. Therefore, we need an ice table whenever we are given an initial information. And at this stage, we were given only moles in a 3-liter container. So remember that anything on your ice tables must be in moles per liter. Right now I have moles and I have 3 liters. I need to divide this to get my moles per liter concentration. Then they've given us an equilibrium concentration for HCl. So I need to know that it's on the E part of my ice table. And I need to know that HCl is the species that I have the information at equilibrium. And they've given me already it in moles per liter, so there's no need to divide this by 3. Okay. Again, make a note that this container is 3 liters, which we will use to calculate concentration for my initial values that are in moles. Then they calculate the value of Kc for this expression. Okay. We need all the values in the ice tables under the E row, meaning products over reactants. I can only do that when this part of my table is complete with information, with concentration information. So now we put it in our ice tables. So right now, we fill in my ice tables, place all the given info in their proper place in the ice table with the correct units. So again, RTFQ. So this 0.6 moles is for hydrogen and it's in a 3-liter container. So now I will get moles per liter. I have 0.720 moles of chloride gas, and then in the same container, 3 liters. And then at equilibrium, the EQ for HCl, EQ for HCl is already 0.03 moles per liter. No need to do division by 3. It's given in the concentration unit. Next, we calculate what we have, and these are our values. Please make sure that if the product's initial concentration is not mentioned in the problem, we assume it to be 0. The next thing we do is find the column that has 2 sets of informations so that I can calculate the change. So here's my 2 sets of information. This column is 2 out of 3 complete. Therefore, I know if I start at 0 and I end up at 0.03, the change must be an increase of 0.03 moles per liter. And remember that once I have a change, I now can use my molar coefficients from the molar ratios to calculate the rest of my change boxes to fill it in. Again, this is 2 to 1, which means that this box will have half of this box. Note that the opposite signs for reactants is opposite of the products. If the products are increased, meaning that the reactants has been used up, reduced in amount. Next, we do the math through the columns of initial minus the change, in this case, gives us this value. And at the end, we have all my equilibrium information for each of the species. So these are the ones that I will use for my equilibrium constant calculation. So I take those values for my E and put them in my expression, which means products over reactants, products HCl, power of 2, ingredients reactants as a denominator with their exponents, their coefficients, and all these values are at equilibrium. I do my substitution of these and receive a value of my equilibrium constant to be 20.0, which means that if it's greater than 1, it favors the products, favors the forward reaction, that the percent reaction is greater than 50%.